Sometimes, when we don't have technology at our disposal, we use a very important rule in statistics called the empirical rule to describe a distribution that we observe might be bell-shaped and symmetric. Take note, the empirical rule only applies to the symmetric or the bell-shaped distribution. Now, to give a context around how to explain the empirical rule, whenever I visit my personal doctor, I am told that the average height is about 70 inches for adult men in the United States. Just about. Then, I am also told that it has a standard deviation, so take note, this is the average. And then the standard deviation is about 4 inches. So rather than use standard deviation, I'm going to use this symbol. To write this symbol, which is the population standard deviation, all you need to do is write the number 0 and then put an extended bar that touches the 0 on top. So this is equal to 4, and then for the average, I'm using mu. Write U and then put a tick mark and then equal to 70. So this is the typical height with a standard deviation of 4. The question though is, do all adults in the United States have an average height of, have an height of 70 inches? The answer to that is no, a resounding one at that. So there will be variabilities away from this average height. Some will be taller, some will be shorter. So how many are relatively shorter than certain heights? Or how many have heights between certain ranges? This is our interest here. So what do? We can use the empirical rule for distributions that have a mound-shaped distribution to approximate how many of male heights are within one standard deviation of the mean, or are within 2 standard deviations of the mean, or are within 3 standard deviations away to the left or right of the mean. This is what the empirical rule does for us. It helps us to approximate proportions of a population that meet a desirable range. And to get us going, we will need, in particular, to note a couple of following. If I have a symmetric distribution, if I locate the mean, if I take one step or one standard deviation from the mean to the right, and to the left, if I take another one standard deviation, well, according to the empirical rule, I am now one standard deviation below and one standard deviation above. The proportion of any quantity in this range is 68%. However, again, using the mean as the reference point, if I take 2 standard deviations forward and I take 2 standard deviations backward, then what we have is something of this sort, and the proportion in that range, according to the empirical rule, is 95%. Then, if I decide, however, to take 3 standard deviations above to the right of the mean and 3 standard deviations below or to the left of the mean, the range or the values we have in that range is equal to 99.7% approximately. This is what the empirical rule means. So, to illustrate, let's consider the next example. In this example, we have been given a data set, and we'd like to start with computing the mean and the standard deviation. You're welcome to look at this data set. I have computed it, and I found the sample mean to be 71.23, and the standard deviation to be 18.07. You're welcome to confirm this using StatCrunch. Key in the data values and As I've shown earlier, compute the mean and the standard deviation. Now, we would like to compute the percentage of data values that fall in each of the following intervals. So, we locate x bar, which is 71.23, and we only take one standard deviation forward and backward, implied by the plus and the minus. So, let's see. So, 71.23 plus 18.07, that will take you to 89.3, that is in the addition. Then subtraction, 71.23 minus 18.07, that will take us to 53.16. Well, this is from the mean. Then, what about if we took two standard deviations? What is two standard deviations here? That will be 2 multiplied by 0.18.07, and that will be 36.14, which is twice the standard deviation. So from the mean, if I take two standard deviations forward, that is a step of or a jump of 36.14 added to 71.23, that will take me to 107.37, and from here, if I take a jump of two standard deviations backward, that will be 71.23 minus 36.14, that will take me back to 35.09. Observe immediately that all of these data values already fall within this range. This is already telling me that all of these data values follow approximately a bell-shaped distribution, since it already conforms to the expectations of the empirical rule. So, with that said, I can answer the next question, which says, does it seem plausible that this data come from a bell-shaped distribution? The correct answer is yes. It seems plausible that it came from a bell-shaped distribution, since it already meets the criteria of the empirical rule that at least within two standard deviations, you already have about 95%. With that question set, we now proceed to the last concept in this topic, and that is talking about z-scores. So, in z-scores, what we're trying to measure is the number of standard deviations a particular value in the data set is located away from the mean or typical value. To compute the standardized value for any value in a data set, we use the following formula. This has a number of pieces. You have x, and the x in this case represents the raw score in the data set. Your x bar represents the sample mean, and your s represents the sample standard deviation, and your z is the resulting z-score. To illustrate what we're saying here, let's put it in context using the first example here. Two students, John and Ali, from different high schools wanted to find out who had the highest GPA when compared to their respective school. Which student had the highest GPA compared to their respective school? The reason why the z-score is very useful in answering this question is that in the different schools, you observe that the different scales of measurement tells us that you cannot directly compare John's GPA with Ali's. John was measured as 2.85, whereas that of Ali was measured on a different scale, and she ranked 77. So how can we compare when you have different scales of measurement? We use the z-score. For John, John's raw score is 2.85 minus, in his own school, the average was 3.0 divided by the standard deviation of 0.7. So this is the z-score for John. And you will get negative 0.2143. Whereas in Ali's school, Ali scored 77. That was our raw score. That was our raw score minus the average in our school, which is 80, divided by the standard deviation in our school, and that will be the z-score for Ali, and that will be equal to negative 0.3. Even though we could not compare 2.85 on a different scale to 77, we can definitely compare their z-scores. And if we look at this on a number line, you'll see that you have the number 0 here. We would have negative 0.2143 here and negative 0.3 here. Well, in this context, bigger is better. Again, context is everything. Bigger is better. So, who has the bigger one here? You observe that the bigger number here is negative 0.2143, which belongs to John. So it means that since higher is better, John has a higher z-score, so he has a higher GPA with respect to his school. So we continue. Let's see another example. In this example, we're to determine whether Grayling Vikings or the Houghton Lake Bobcats had a relatively better run-producing season. The Vikings scored 777 runs and play in Division B for high school baseball, where the mean number of runs scored was 677.4 and the standard deviation was 51.7 runs. However, the Houghton Lake Bobcats scored 775 runs and play in Division C for high school baseball, where the mean number of runs scored was 640 and the standard deviation was 55.9 runs. In order to answer this question, the first note we should make is that they play in different divisions. So, the different levels of difficulty, we cannot compare the raw number of runs. That would not make any sense, since the different divisions have different difficulty levels and different existing circumstances. But what we can do is use the z-scores for each of these number of runs. So for the Vikings, this is what we will do. For the Grayling Vikings, we'll get their own z-score. How? We'll take their raw number of scores, which is 773, minus the average in that league. So let me erase this. The average in that league was 677.4 divided by the standard deviation, and that will be equal to 95.6 divided by 51.7, which is 1.8491. And then for the Houghton Lake Bobcats, you have the z-score, which is going to be how many, what was the raw number of runs, 775, minus the mean, which was 640, divided by the standard deviation, 55.9. And this will be 135 divided by 55.9, which is 2.4150. So on the same scale, you have 2.4150 and you have 1.8491. Based on context, we want the one which is higher. So Bobcats seem to have a higher. In this case, we can say that the Houghton Lake Bobcats had a relatively better run-producing season in their division. We now proceed to the next question, or example. One year, the fastest male runner ran the Boston Marathon in 127.95 minutes. Among all men in the race, the mean finish time was 227 minutes with a standard deviation of 47 minutes. That same year, the fastest woman ran the Boston Marathon in 143.52 minutes. Among all women in the race, the mean finishing time was 248 minutes with a standard deviation of 43 minutes. Who did better in relation to gender? Well, since they run in different in different scenarios. For the males, the fastest was 127.95. I am going to subtract the mean of 227 minutes divided by the standard deviation of 47 minutes to get the z-score for the male, the fastest male runner. The answer here is negative 2.1074. Then for females, the raw score was 143.52 minus the mean of 248 divided by the standard deviation of 43 minutes. That was the z-score for females, and this will be equal to negative 2.4298. So I'm going to put both on the same scale now. So I have negative 1, I have negative 2, I have negative 3. So somewhere between negative 2 and negative 3, I have first negative 2.1074, and then I have negative 2.4298. Well, in this context, finishing in lower time is better. Finishing in lesser time is better. So I want the lesser of the two. The lesser of the two, since they are negative numbers, is negative 2.4298, which pertains to the female. So I have an answer for this question. Who did better in relation to gender? The fastest female runner did better in relation to their gender.